Hello and welcome to calculus number 3, and this is about limits and derivatives, and we're going to be continuing what we talked about in the previous video. So last video we saw how we shorten the domain and the range. Well, actually it's just the domain we shorten and then we make it smaller and smaller and smaller and smaller, and that's how we found the derivative. Let's say we were going to find the derivative at the point 1. So what we did was we shortened the domain a and b into the closest value possible, the nearest two values bigger and smaller to 1, so that we could see the instantaneous change at the point 1. That was the main idea in the previous video. And today we're going to be talking about equations and some problems. So a derivative function means it's a function that shows the rate of change of the original function. So for example, a derivative of a distance is speed, because speed shows how much distance you go per unit of time, per second, per minute, per hour. You see in your car, when you're in the car, you see what's the speed of the car, Dad? Then it's like your dad would say 40 kilometers per hour or 60 kilometers per hour. That is the rate of change of distance the car goes per hour. And derivative of speed is acceleration. At what rate of change is the speed increasing? That's the acceleration. This concept is a very typical concept in physics, kinematics, which you'll learn in the future, or right now you may, or potentially you already know about it, which makes it easier for you to understand. So a derivative function is whenever you have a derivative, you always put that little dot on the top between f and the value. So that's how it does, like f slash out a function of derivative function of f a equals limit, where h is the point you choose in the graph, in the equation. Limit of as h approaches to 0, f a plus h minus fa over h. This is a typical and a general derivative function. The reason why I said it's a typical one is because there's another way to express derivative, which is this. A derivative of fa is equal to limit where x approaches to a, and fx minus fa is equal to x over x minus a. The way how you could understand this function is pretty similar to the way I explained it before. You decrease the domain closer to 1, and then as you have a smaller domain, as you have a changing domain, you also have a changing corresponding y values, and so this is how the way that derivative works. So this is another way to express derivative function. So let's solve some examples and problems. Find the derivative of the following functions at the point 3. Solve it first, and then we'll be checking the answers later. And that is why it meets the second condition, because we're talking about limits. We're not talking about the actual f2, the function f2. So the third condition, limit of x approaches to a fx equals fa. Does this happen? No, because the limit as x approaches to a fx is equal to 4, but f2 in this function is divided as 4.2, so 4 does not equal to 4.2, and that is the reason why we can't apply derivative to this function at point 2. So in all functions, there are continuous functions and there are incontinuous functions, as the one we just saw. And if function is continuous, then we know that it could be derived. But the thing we have to care is that just because a function can be derived doesn't mean it is a continuous function. This equation, this logic does not always make sense. You might think it's weird because a derivable function is within the continuous function, then logically, if it can be derived, it should be continuous. So at which conditions or which type of specific function does not make this logic work? That all derivable functions should be continuous. I'll tell you the answer and some other functions that shows this situation. Until we meet in the next video, I want you guys to find yourselves what functions apply this logic that all derivable functions are not always continuous.